Hi and welcome back to Module 8, Applying Chemical Ideas. Today our video is discussing analysing a NMR spectrum. So already we've talked about a number of different things. We've looked at the different NMR or the unique environments of the carbon-13 and the proton or H NMR. And the peaks that we'll see will be based on the number of different unique environments that carbon or that hydrogen has. And that was the topic of our last video. How do we know where those peaks will occur and what they correspond to? And that is the topic of today's video. So let's get started. Now, when we're looking at our spectra, you're going to often see TMS at our 0 point, and that's our standard for reference. So like a baseline there that we can use the TMS to compare the chemical shift that the atoms have experienced due to the different environment that they're found in. Now, TMS stands for tetramethylsilane, and it doesn't actually provide any information at all about the standard that we are, or the sample that we are testing. It is purely there as a reference point for a zero reference point. So on our NMR, we are going to see sharp peaks, and those peaks are going to correspond to either a particular carbon or a particular hydrogen, depending on which spectrum we are looking at. And each peak is going to represent those different unique environments that we have. So if we have two unique hydrogen environments, we will see two peaks on our spectra. And when we're looking at those spectra, you'll notice that the scale on the x-axis may be a little different to what we've seen in the past, and the x-axis increase to the left, so 0 is to the right, and the scale moves to the left from the TMS 0 point. So we're going to be looking at chemical shift, and you heard me mention that before and probably didn't understand what I was talking about. But our chemical shift is where we will have the different spin states of a sample compared to the energy needed to change the spin states in the TMS. So how much energy is required to change the spin from being aligned to not aligned with the direction of the magnetic field of the TMS, compared to how much of that energy is required to change the spin for the sample that we're looking at. And that difference is called the chemical shift. Now, it's measured in ppm. Sometimes we will see that lowercase delta sign being used as well, like a writing D, I suppose. So then we're looking at shielding a little bit here as well. And so the actual magnetic field that the nucleus experiences isn't necessarily the same as the amount applied by the device or the magnetic field that the NMR has. And this can be because electrons themselves, as you would have remembered from one of our earlier topics in Year 11, have their own spin. And when they have their own spin, they also have a magnetic field, and that shields the nucleus a little bit from the applied magnetic field. So we've got this magnetic field being applied by the NMR, so a big electromagnet, but not all of it gets to the nucleus. The electrons around the outside may shield that nucleus from all of that applied magnetic field, and that will be sometimes evident in the spectrum that we have a look at. So when we're looking at these, obviously carbon atoms are on a carbon NMR and protons are on a proton NMR. We're not going to see them on the same spectra. However, what you'll notice is when you're looking at the NMR, you'll usually notice that the H NMR or the proton NMR is usually in the range of about 0 to 10 ppm on the x-axis, so their chemical shift will be about 0 to 10, whereas the chemical shift for carbon atoms are usually in the range sort of between 8 up to 220, 230. So the range is quite different. So when we're seeing the 0 to 10 ppm, we know we're dealing with those hydrogen atoms that are there. And when we're looking at the carbon spectra, we'll usually notice that the chemical shift for carbon atoms is usually in the range of 8 to about 220 ppm also. So let's have a look at a couple of different spectra. Here we have the carbon NMR for chloroethane. We need to be able to interpret this graph whether we've got the structural formula next to it or not. So we need to consider that while there's two peaks there, if there were identical chemical environments, there would only be one carbon peak. So this is telling us that there is actually, in fact, two different carbon environments there. So let's have a look at this. What have we got? We have got a carbon atom here with 3 hydrogens off it, and it's also attached to another carbon. Yet on this carbon here, we have got carbon with 2 hydrogens and a chlorine attached to a carbon. So they are surrounded by different atoms, and that's going to make a difference in the energy required to flip it, and therefore that's going to be seen as 2 different peaks. And we can see that here where we have our TMS over here at 0, so it's our benchmark. We have got one of our carbon environments here, which actually corresponds to this one, the methyl group. And then we have this one here, which is corresponding here to the ethyl, the 2 hydrogen groups there and the chlorine on the side. So let's look at the proton NMR for this one. So in this case here again, we have got 3 different hydrogens attached to a carbon. That's going to produce its own environment, whereas this one here, we've got 2 hydrogens with another chlorine there, and that chlorine nearby is also going to have an effect on the energy that is required to flip the spin in alignment and produce a different signal again. And we can see that's come out here. We've got again our TMS that you're going to see on all your samples. Now a methyl group is found here, so you can see that corresponds with this one here. This is our first group here, and these 2 hydrogens less intense in terms of the height of its peak, and that is a different and unique chemical environment. So these are quite complex, and it's taken quite a bit of reading of different resources to get my head around it. You're going to need to do the same, and the only way you're going to do that is to read your textbook, look at other sites if that helps you, but also practice and asking questions in class. Reading the spectra, once we become more familiar with it, you'll find it's no more difficult than the other 2 spectras we've already had a look at it. And the only way we can do that is to practice, so we'll do that in class. See you then.